So, complex numbers. Just so we're aware what we're going to be avoiding. What is the square root of -1? I bet your optometrist knows. Yes, nice. Okay. How about the square root of -4? Try again. You're getting warm. 2i. Yes, yes. Right? How about the square root of -2? This is a gruesome mathematical term. Okay, this is referred to as gouging the eye out. I radical 2, right? The 2 you can't do anything with the square root of it. The 2's trapped inside, but the square root of -1 comes out and becomes I. You know, so that's the gruesome term, gouging the eye out. Well, depends on who you are.
Wait, is it I2?
I radical 2, sorry if that's poorly drawn or written there. Square root -16 would be 4i, yes. Oops. That's true. We're going to be avoiding those types, those solutions. While they do give our solutions to a polynomial function, they don't show up on the x-axis, do they? What kind of solutions show up on the x-axis? The reals. Okay. Now, the fundamental theorem of algebra is important to us. In this situation, the polynomial function, some of you, I didn't take off on your last test, but a polynomial function does have a dependent variable, and some of you had no love for y equals. So you did all the right stuff. You found the zeros. You multiplied them all out. Fantastic. But it really wasn't technically a polynomial function. I didn't take off for that part. In the future, that's probably like a half-point deduction if you have no love for y. Don't forget about y. But a polynomial of degree n has n complex zeros. Some of these zeros may be repeated. What does that sound like? Starts with the letter M. Multiplicities, right. Basically, what they're telling me is that I can, if I add up all the zeros with their multiplicities, you have to take into consideration their multiplicities, you get the degree. I mean, that's if I take into account all the reals and the non-reals. We're going to stick with the reals. A lot of this we've already kind of discussed. Polynomial functions. The degree has to be positive. Has precisely n linear factors. And there's a big word here, if. You could break things down into linear factors, as long as you're willing to go all the way to imaginaries. If we stop shy of that, we'll have instructions for you on that. But you can break everything down. Now, I know this is going to contradict a few things that we did in Algebra 2, and you will feel like we lied to you a tad bit in Algebra 2. We were trying to protect the innocent. But now, we shall let you in on more secrets. I know, every year you find out more secrets about stuff. You know, like asymptotes. There's no function that crosses its own asymptote. Total lie. But, you know, what? It's a good definition for end behavior, It's a bad definition if we're talking about the entire function, including what's happening near the origin. But it's a different conversation. We haven't dealt with a lot of those functions yet. You'll see them later. Write a polynomial function, all right, that good old y equals thing, of minimum degree in standard form. We'll start with factored form first, so that's where we'll begin, and then we'll change to standard form. Real coefficients, okay? We'll probably even go further than that and say integer coefficients. So, you know, we'll go even a step further than just real numbers. I'll add that in. Whose zeros include -3, 4, and you see that I got rid of the complex one and I exchanged it for 2/3. What's the minimum degree for this? Third degree, right? I clearly see 3 zeros. They never said anything about multiplicities higher than 1. Although that would definitely make the degree higher. But if we want minimum degree, then they all have to have multiplicity 1. Okay? Pretty sure you know what to do with the first two. Interested to see what you do with the last one. Remember, I don't want any fractions, only integers. So, write down the factors. I know you got the first two. For -3 and +4, yes. Now, what are we going to do with that last one? Get your x's. So, that's great, that's great. That's the one we need to, that's going to give me fractions if I do that. Now, it's true that that is a form of an answer that will work, but it doesn't have integers. So, what can we do to that one? Yes, yes, yes. Yes, you're getting there. Yes, that's it, right there. That's it. There you go. Okay. What are the 3 factors? Okay, good on the first two. Now we got to figure out that last one. No fractions. No fractions. So, good, good. We got to think about that. That's 2. So, how do I 2/3 but see, he's close, but not quite. Okay, so if you look at his last factor right there, that's close, but not quite, because his actually gives him 3/2. Okay, she's got it behind him. You're not figuring somebody else. Alright, so you know that this, you do x minus 4, so a lot of things that does. Okay, so I saw a lot of you x plus 3 and x minus 4. Why is this not correct? X minus 2/3. Because if we're required to have only integers, that would cause me to have fractions. So what do I do to that last one to make that have only integer coefficients? Multiply by 3, and several of you were doing that. 3x minus 2. Okay, now put it in standard form. Go. I don't care if you use boxes or no boxes, whatever's comfortable to you. There's probably something like that. 3x minus 2, 3x minus 6. 3x minus 6 would have. Yes, yes, yes. Yeah, yeah, no, yes. You get a minus 36x and a positive 2x. Oh, that was good. I was going to say, you got all the right pieces there. Yes, yes. Again, why? I mean, you had it up here. Yes, yes. I like it. Good. I like it. Except, what happened to Y? Okay. So, don't forget Y. Whether you use boxes or draw arrows or whatever makes you feel comfortable in doing this process, pick 2, multiply them together, and then multiply times the last factor. Now, yep, you just copy in, or do you have a question? There won't be any XY. So that should be 3x. So, all right. If you just want to jot down the final answer and then go back and fill it in, that'll work. Okay, our factoring is going to combine a lot of things that you've done in the past. A lot of your Algebra 2 skills are going to come together. Every polynomial function with real coefficients can be written as a product of linear factors. Well, you know that we just wrote it as a product of linear factors. 3 linear factors. But did you know that there are things called irreducible quadratic factors? Irreducible, nice word there. Use it at a party. Irreducible as long as you only want to stick with real coefficients. If you open the doors up to the complex numbers, then we could reduce those things. But we're not going to. We're going to stop. Okay, might I remind you of, let's say, how do you factor x squared minus 9? Just as this was a quick algebra 2, maybe and definitely algebra 1. X minus what? X minus 3, x plus 3, right? Okay, that kind of thing is definitely going to come up in this next question. How about, can you factor something like this? X squared plus 4x plus 3. Can you factor something like that? What does that factor into? X plus what? 1? X plus 3. Okay, how about x to the 4th plus 4x squared plus 3? That's called a hidden quadratic, which you also did last year. Now, if you look at these two examples, you might see some similarities. Talk to your neighbors right now and see if you can apply some logic there and factor the hidden quadratic, which you probably haven't done in a while. Talk to the people. Whatever your guess is, foil it out and see if it works. So you had a guess. Try it. See if it works. Yeah, I'd like to know what you think. Hey, nice job. You do remember your hidden quadratics. Well done. So what do you think the connection is between them? Come on, some of you have already told me the answer. X squared instead of x. Still a plus 1 and a plus 3. Now, can we factor these things? The answer is yes. Now, we lied to you last year and told you no. We kept saying, like, you can't factor a sum of squares. The only way that that's a true statement is if you are only dealing with real numbers. As soon as you allow yourself to go into the complex, which we're not going to do, then you can factor those things. What do you think those would factor into? If we allow ourselves to use complex numbers. Just take the x squared plus 1. What do you think? X plus and x minus, what do you got? Think outside the box. Okay? Now, just to prove it to you, even though we're not going to be doing this on tests and stuff, so the product inside here is xi, right? What's the product outside? Negative xi. What happens to positive xi and negative xi when you add them together? Gone, right? Magic. Okay, how about I times negative I? I times negative I. I squared is negative 1. Keep that in mind. But this is not I squared. This is negative I squared, isn't it? So the opposite of negative 1, what do we call that? Almost.
Positive 1.
It is possible to factor these if you're going to go down the road of complex numbers. We're not. So guess what we're going to do? We're going to call this an irreducible quadratic. Now, that should be music to your ears because that means you need to stop. Right? If we're not allowing ourselves to go past the real numbers, this is as far as the factoring goes. Even though we know we can go down to farther linear factors, if we say that we're going to stop with real coefficients, boom, that's it. Irreducible quadratic, what about this one? Irreducible quadratic. We tried to get those reducible ones when we were in Algebra 2 so you could continue factoring because we didn't want to mess with these situations. Okay, now, I got this quintic polynomial, right? 5th degree polynomial. It says I'm supposed to write this as a product of linear and irreducible quadratic factors, each with real coefficients. Okay. Now, how do you find the factors? Some of you knew this on your test and some of you didn't. I mean, I told you it was going to be on there, the rational root theorem or the rational zeros theorem. So how do I look at this polynomial? Something to do with the 16 and something to do with the 3 to find the possibilities. What do I do with the 16? Something to do with the 16 on the top and something to do with the 3 on the bottom. Oh, the factors of 16. Do you know any numbers that go into 16? 1, 2, 4, 8, 16, 32. Who was that kid? Okay, so all over, what are my factors of 3?
3.
1 and 3, right? Now, that creates a lot of possibilities, doesn't it? Now, if you didn't want to go plug in all those possibilities to find out which one's going to give you 0, what could you do? I got this polynomial. What am I going to do to find 1, 0? Graph it. I like it. Use that graphing calculator, right? And if we did that, we would find that 2/3 is one of the zeros. So either I found it on the graph or they gave it to me right here. They told me that 2/3 was one of the zeros. Okay, what am I going to do with that 2/3? Plugging it in won't help me, folks. Synthetic division, excellent. Okay, give me those coefficients. 3, -2, 6, -4, -24, and 16. Man, I know. Who made a question like this? Don't tell me it was me, because I didn't. Okay, so we carry down the 3. Now, without a calculator, can you tell me what 2/3 times 3 is? Please? 2! Yeah, because the 3's cancel. For those of you wondering how we just did that, 2/3 times 3, we watched that in our minds, right? So it's a 2. Write that down up here, and we add. Now, I was a little concerned when I saw some people in their synthetic division immediately subtract these 2 values. Well, guess what? That screws up the rest of the synthetic division. I saw some people subtract 1 and then they made sure to add all the other ones. I was like, okay, well, the one that you subtracted caused the rest of them to be wrong. Just keep in mind, it's multiply, add, multiply, add, multiply, add, multiply, add until you get done. And what should you be looking at down here? What should you be looking at down there? 0, thank you, right? Because it's supposed to be the remainder when you call it a 0. Okay, so when I add those two together, what do I get? 0, okay. So multiply and add. Anybody know what 2/3 times 6 is? That's 4, yes, that's true. And you add down that column and you get 0. And you multiply again and get 0. And you add and you get negative 24. And what's 2/3 times negative 24? Negative 16. Yeah. Okay? And we add and we end up with 0. Fantastic. What in the world did we just find? If this is the remainder, what's the next one over? The constant. And what's the next one after the constant? The linear term x. And what's the next one after the linear term? The quadratic term. And after the quadratic, the cubic. And after the cubic, the quartic. Folks, that's what you get. Notice that it's got 2 missing terms in it. Now, I'm asking you to factor this part right here. What do you notice about this thing? Take out a GCF. What is the GCF? 3. Okay, all right. Yeah. Pull out that 3. Now, the next thing I'm going to tell you or show you is not really absolutely necessary when factoring this thing, but what could you do with these? You could distribute, right? And if you distributed, what would you get? 3x minus something. 3x minus 2. Okay. Okay, so what is this? Whoa. What is this thing over here? Isn't that one of those hidden quadratics? All right, so what does that break apart into? Right, you got x squared and x squared. Okay, now I need factors of -8, or factors of 8 whose difference is 2. Plus 4 and minus 2. Which one of those is irreducible? Tell me, talk to your neighbors. You got about 15 seconds to figure out which one of those is irreducible. See what they think.
Oh, yeah.
All right, which one do you think is irreducible over the real numbers? X squared minus 2? Sorry, that is reducible. The irreducible one is right there. Ah, x plus or minus 2, you're talking about x plus 2 and x minus 2 like this? Okay, but that would actually give me x squared minus 4. Ah, yes. So if we change this to, x plus 2, right? Then of course you're going to get a middle term of 4x. So, okay, now, if you go back to the thing that you did not want to look at earlier, that x squared plus 1 thing that we did, where we broke it up into this, how could you use that logic with x squared plus 4? I'm not saying that I'm going to ask you to do this, folks. But that would be x plus 2i and x minus 2i if you're allowing yourself to go all the way. If you allowed yourself to go all the way to the complex numbers, you could factor that x squared plus 4. But we're not. We said we were stopping with just real numbers. So, gone. Oh, I almost got it all at the same time. Yeah, I'm not going to worry about it. What about the x squared minus 2? What's that going to break up into? Now, wait a second. You said at the very beginning of this lesson that x squared minus 9 broke up into x plus 3 and x minus 3. So why can't we use the exact same logic on this question? So, what did you do to 9 to figure out that you were going to use 3? You took the square root, thank you very much. So that means we could factor it into this. Now, we said we weren't going to do imaginary numbers, but nobody said we couldn't do radicals. Okay? So that's why the end answer is the way it is down there. You had your linear factor 3x minus 2. You had another linear factor of x minus radical 2 and x plus radical 2. And you had the irreducible quadratic x squared plus 4. Yes, folks, this is going to be factoring on steroids.
So we don't want numbers.
We're not going to go past the real numbers to imaginaries. We're going to stop right there. Those 4 factors, we're going to call it quits when we get to that irreducible quadratic. Now, it's x squared plus 4, and you know there's lots of kids who are going to bite on that because they see a perfect square. Because they're so used to the x squared minus 4, which does factor into x minus 2, x plus 2. I know, it's kind of an evil trick. Polynomial function of odd degree. Every polynomial function of odd degree with real coefficients has at least one real zero. How do we know that? What do you know about the end behavior of odd degree polynomials? Very common in the 1970s. Very common in the 1970s. Yes, the odd degree polynomials were opposite end behaviors, right? Yep. Okay. And so, what are they going to have to do eventually? Cross the x-axis. Thank you very much. So, they will at least have one real zero. I know, well. Question 13. Write a polynomial function of minimum degree in standard form with real coefficients whose zeros and their multiplicities include those listed. Let's at least get it in factored form first. Let's go with question 13. By the way, I will pick some problems. I haven't had a chance to really pick a few problems from this section. 2-5. I have to be very specific because I don't want to use the ones that end up giving you imaginary results. Because we're sticking with just the reals. Let's see if I can pick one out. Maybe I should just make one up. I should just make one up. It's for you to factor after you get done with this one. Hope I don't screw this up. At least get it in factored form for me. Dang, these things take a long time. So in factored form, we would have what? X minus what? 1? All right. Somebody said squared? Oh, well, you're right about that. Yes. Whoop, whoop. Then what? X plus 2? Quantity cubed. Don't say x plus, because if you say x plus 2 cubed, somebody might think you meant that. That ain't what you wanted. You wanted quantity cubed. Right. You don't want to be thrown out of a party for that kind of stuff. Okay, now, if it had to be in standard form, yes, we would need to go further, and we would need to start multiplying all that stuff out. All right, I want you to write down a polynomial to factor tonight. And let's just pray my multiplication isn't wrong, since I did it quickly. Just making sure I didn't screw something up there. Okay, now I will give you one hint to start. Okay, x equals 1 is, we're busy.
Pardon the interruption.
No.
Just a reminder, there is after-school detention tonight. That'll be down in the cafeteria from 2:45 to 4:45. There's no community service. Those of you that have after-school detention tonight, please report to the cafeteria no later than 2:45. Thank you.
Okay. What would you do to start this problem? If you knew that x equals 1 was a 0. Synthetic division? Okay. Glad you're still with me and not leaving already. I feel neglected at the moment. What is the deal? Seriously, I'm like, if we were working on homework and you were doing your own thing, I guess I could understand that. If your leg was broken and you had to leave early, then I could understand that. Wow, I just...